So you want to prove that this is true for all these values of n. So the idea is then that you want this equality to be true for all the values of n. The way to prove it is to prove that is true for the first value of n. That is what you did. You show that in the first part here, when you put n equal 1, you just get here 1. And in the second part, when you substitute 1 here and here, you also get 6 over 6, that is equal to 1. So then it is true for the first element. That means in your line of dominoes, all the dominoes that you have here, means that the first domino falls. Okay, so once that you prove for n equal 1, what is not correct in your problem is the proof of the step of induction. The induction step, what says is that the hypothesis is that this is true. I mean, the formula is true, not for all n, as you said, because if it were true for all n, you wouldn't be proving anything. I mean, that is true for all n is actually what you need to prove. So you are not going to assume that that is true. What you are going to assume is this thing is true only for n equal k. What does it mean? In your first, in your line of dominoes, this is the domino that is in n equal 1. So the one domino that is in n equal k, so this one, you are going to assume that is falling. Okay? Not all the dominoes, as you said. No, this is what you need to prove. It's not what you are going to assume. What you are going to assume is only false the domino that is in place k. Okay, so then, and what means in terms of the formula? Well, you are going to assume that this formula is true when n is equal k. And as you said, it should be substituted everywhere. Where there is an n, should be a k. And so this is this formula then, the one that you are assuming that is true, is this all the way until k squared, and now k plus 1, 2k plus 1 over 6. So we are assuming that this formula is true. So that is going to be our assumption, that this equality is true. So this is an assumption. We assume that this is true. And the thesis is very different. We are not assuming. The thesis is what we want to prove. We want to prove that the formula for k plus 1 is also true. In terms of dominoes, you know that the first one falls, and you are assuming that the one that is in place k, this is falling. That's the assumption. Now, the one that is in place k plus 1, this one, you don't know if it's falling. This is a question. So that is what you need to prove. See, that's the difference between assuming and proving. The k, we are assuming that is falling. The k plus 1, we need to prove that it falls. Okay, so let's write down what we need to prove. I mean, what we don't know yet that is true. So this formula now for n equal k plus 1. And as you said, everywhere where you see an n, that one should be substituted now by k plus 1. So in the left part will be there k plus 1 squared. But in the right side, you should be substituted the 3 times that appear. So in this case will be k plus 1 when we substitute this 1, and then k plus 1 when we substitute here. That will be k plus 2. And then here is more complicated. I'm not going to do the operation directly. I'm going to write down. This will be 2 times k plus 1, right? So I'm going to write down that 2 times k plus 1 plus 1. Let me write it smaller. I don't have room here. So that will be here. Start over will be k plus 1 times k plus 2, and so the last one will be put in there. K plus 1 will be 2 times k plus 1 plus 1, okay, over 6. So that is that is what we don't know if it's true. So that is what we want to prove that is true. See the difference? Here is proved, here we want to prove it. We don't know yet if it's true or not. And how we are going to prove if it's true or not? Well, we are going to use what we know. We know that this is equal to all this. So the idea is to observe that in all this expression, actually, that we don't know to what equals yet, we can observe that if we stop here, one before, the one that is before k plus 1 here should be exactly k. And so that means that this is exactly what we have here. And by hypothesis, we know that this should be equal to this. So then if what we are going to write here, we know, because we know this equal here, this is equal to k plus 1 to k plus 1 over 6. I mean, I'm just copying exactly this. Okay? And the remaining, I leave it the same, plus k plus 1 squared equals to all that. Okay? So just copy the same thing. Let me write it again, k plus 1, k plus 2. Here I can do the operation already. That would be 2k plus 2 plus 1 would be 2k plus 3 over 6. Okay, so this now is just algebra. So now you need to add this, do this operation, and do this operation, and just check that are the same. That's all what it is. So here is in the left part is a fraction, common denominator is 6, so the numerators are going to be k plus 1, 2k plus 1, and copying the same, and here would be 6 times k plus 1 squared, right? Yeah, this is just common denominator with fractions. In the other side, for the moment, I just copy as it is, because now at each step, you should be just looking is what we have in both sides is the same or not. So one that we copy here, let me see if I have room to write everything here, k plus 2 to k plus 3 over 6. So at each step, you should be observing if whatever is appearing here and here are the same. At this point, we see that they are similar but are not the same. We see a 6. We can simplify since it's the same in both sides. But the numerators, we are not sure if they are the same or not yet. So let's just do now the remaining is just do operations here. Do the algebra here, the arithmetic, and see if we get exactly the same in both sides. So doing the arithmetic here, we can observe that in these two terms of the addition, there are factors that are common, right? One factor k plus 1 is common. So I'm going to take it as a common factor here. Let me take this k plus 1 as a common factor, and in the first term remains this. So that will be here k 2k plus 1. And in the second part remains a 6 and another k plus 1. Okay? So that is by taking as a common factor k plus 1 from these two terms. And in the other side, for the moment, I leave it as it is. I'm just copying the same, k plus 1, k plus 2, 2k plus 3. Okay, we observe already here that there are now two things that are the same, right? K plus 1 and k plus 1. They cancel, they are the same. So let's check this, and let's see if they are the same. Well, let's just do the operations here. Let's do distributive. So that will be 2k squared plus k plus 6k plus 6. And in the other side, let's do distributive also. That will be k times 2k, 2k squared, k times 3, 3k, and now plus 2 times 2 is 4k, plus 2 times 3 is 6. Let's combine like terms. This is 2k squared. K plus 6k is 7k and plus 6. In the other side, let's combine like terms. 2k squared. 3k plus 4k is 7k plus 6. And now observe are exactly the same in both sides, so that means that the identity is true. So that means that the domino in the position k plus 1 really falls. And so then what we have proved is that the first domino, the one that is in position 1, falls. Then you prove it that assuming that k falls, the k plus 1 also falls. And according to the theorem of induction, that means that all the others are going to fall. So that the formula is going to be true then for all n, even though you prove that only k plus 1 is the one that is falling. So that is what induction says, that even if you prove that every time that one falls, the consecutive falls, so then that means that all of the dominoes will fall.